Okay, in lesson 2.3, the structure of the atom, we are going to study the wave and particle duality of electrons and the experiments that led to that proving this. And we're going to look in detail of what the atom is like based on the quantum mechanical model. So I'm going to give you a brief summary in part 2 of the quantum mechanical model, and then in the next 2.4 we are going to analyze details. So first we are going to watch a video. I'm going to play it. It's by Dr. Neil Johnson. He's explaining the wave-particle duality in the Royal Institution Christmas lecture series. If you like, you can watch these. These lectures have been going on for like 200 years. And the modern ones are on YouTube.
Our story starts with a duck pond. And with this man, Thomas Young. Because about 200 years ago, he was sitting by a duck pond, watching some ducks. I have here a pair of ducks. I want to have a look at what Thomas Young saw. Just wind up my ducks. What he saw, as the ducks swam around, was a pattern appear in the water, which you can see down here. Now the pattern was caused by ripples on the water, leaving the ducks and interfering with each other. You can see it in a more controlled way. Here we have a motor that's actually going to cause ripples, and it's going to pass through two slits, and these slits are going to produce ripples which go out into the water and actually interfere, very much like with the two ducks. You can see a pattern emerging. You can see here, along this line, two ripples are adding up. So you're getting bright and dark lines. But here, it doesn't look like anything's happening. That's because the waves, the ripples, have actually cancelled each other out. Now, this made him pretty happy. First of all, because he liked ducks. But second of all, because it reminded him of an experiment he'd done a couple of years earlier with light. I'm going to show you now what he saw with his light experiment. Here we have something very similar to the pond and the two ducks. Actually very similar to that tank with water and the two slits. Because here we have something that produces light. And the light passes through two slits, actually very close together, because light is a very short wavelength, a very small wave. So you can't actually see these two slits, but it's the same idea. And then the light passes on and hits this screen. You can actually see a pattern that's quite similar to what we saw on the tank with the water. And there are regions of bright and dark and bright and dark and bright and dark. So this set him thinking, well, if I saw the same pattern as I saw on water, I know that waves travel on water, that must mean that light is a wave. After all, particles wouldn't do this. Let's have a look at what particles would do. For this, I need a volunteer with a lot of puff. Could you come down? Your name is? Jay. Could you stand here? Now, what you're going to do is you're going to blow through this tube, and here is sand. Now, sand consists of grains, particles, lots of them. And they're all packed in here. And as Jay blows, he's actually going to blow sand through this box, up against these two slits, and the sand can pass through these two slits, very much like two slits we had with light. And on the back here, we've got a screen, which is going to collect the particles of sand as they go through the slits. So, huff and a puff, and blow through the tube, Jay. Keep going. Great. You can do it a little bit less. That's it. That's great. Thanks very much. Go back to your seat. I'm just going to show you what's on the screen. And this is it. It's not really a surprise. There are two stripes, very much like the two slits. So, of course, sand consists of grains, like little particles, and they either go through one slit or they go through the other slit. And that's what you're seeing. These particles have gone through one slit, these have gone through the other slit. So this is what sand does, and this is what particles do. They produce this pattern, and it's unlike the pattern that you get with waves. Now we're going to try something a little different. We saw the pattern that light produced, nothing like the sand. But here we've got essentially the same piece of equipment as before, but we're going to turn the brightness of the light down. Here we have the source of light over here. And it's passing through two slits. We've had to cover this up because we don't want any light to get in. The light passes through the two slits, goes over to the other side. Instead of a screen over here, we've actually got a camera because this detects really low levels of light. I'm going to see what we see. Actually, up there on the screen, you can see what the camera's picking up. The first surprise is it's picking up dots, blips. This is light traveling through this, but it's arriving as blips, like the sand, as particles. So that's amazing. But have a look at this. If we collect up all these blips, collected over a time period, and have a look at what the pattern is, we see something quite remarkable. The pattern you see is the pattern that waves make. But the light arrives in blips, in packets, as small particles, which physicists call photons. So this is incredible, because the light's traveling, making a pattern as though it were going through two slits. Because remember, to make that pattern, that wave pattern, there've got to be two sources, two slits. The light's got to go through both slits. And yet it's arriving as a blip, as a particle, like the sand. This is the essence of the weirdness, of the spookiness in the quantum world.
Okay, so I hope you found that interesting. So when he first looked at water waves, the two ducks, the two water going through double slits like this, dual slits, converged together and made a pattern that sometimes cancelled each other, and then he sent light, and you saw light had that same interference pattern when you sent out an intense, very strong beam of light. Then he got the kid to blow sand, which was particles, through two slits, just as the light did, but then you saw mostly sand going through just two slits, sometimes one more than the other. But you didn't see an interference pattern like a range of beams. So in the quantum realm, things happen really in a very spooky way. So what is the quantum realm? It's the smaller than atom region. So in Newton's physics applies to objects larger than atoms, but when you have objects smaller than atoms, Newtonian physics doesn't apply. It's quantum physics that applies. And it is another area entirely, and it is a very spooky area. It's very weird. Logic doesn't apply. Anyway, so now in 1925, Davison and Germer did this double slit experiment, the same one you saw, but instead of light beams, they shot a beam of electrons through two slits. So what they expected, if electrons were indeed particles, you will see two patterns right on the opposite side of these slits, like you saw with the sand. But this is what they saw. They saw a diffraction pattern that produced fringes, just like the waves do. So the observations show that individual dots on the screen indicate that single electrons move like particles, just like in the video we saw when you had the weak intensity light, you saw dots. But when you measured all the dots, you see, like in number 2, an interference pattern indicating that electrons have wave-like properties. So the conclusion, when you combine these two observations, is indeed electrons are both waves and particles at the same time. So we're going to look at the summary of the quantum mechanical model. Here's a model of the atom based on the quantum mechanical model. Protons in red, neutrons in blue. They're actually colorless. Atoms are spherical and mostly hollow inside because of the electron cloud. Atoms are divisible, made up of 3 subatomic particles. The electrons that are negatively charged, protons that are positively charged, and neutrons that are zero or neutral charged. Protons and neutrons are similar in size and mass, but electrons are 2000 times smaller. The tiny but dense nucleus is made up of protons and neutrons and is surrounded by a cloud of constantly moving electrons in an electron cloud. 4 neutrons and the strong nuclear force keep the positively charged protons tightly packed inside the nucleus. 5 electrons have both particle and wave-like properties and thus cannot move around the nucleus in orbits. So electrons are found in 3-dimensional regions of space called orbitals with a 90% probability of finding them. 6 electrons are held in place by their attraction to the positively charged nucleus. 7 electrons can move from one energy level to another by absorbing or losing a quantum of energy. 8 neutral atoms have an equal number of protons and electrons, cancelling the charges, giving them a zero charge. Number 9, atoms combine in whole number ratios to form compounds, and atoms cannot be created or destroyed in chemical reactions. Remember that. However, new elements can only be formed in nuclear fusion or fission reactions. We will talk about that in the next another unit. And that's it for now. Please memorize all of these. Just commit them to memory. And here are S, P, D, and F orbitals. These are the 3-dimensional shapes in which electrons hang out. Those are electron houses, if you want to know. We'll learn more about them in a lesson soon after. That's it for now. So you would be interested to know that we can actually today see individual atoms in compounds using the scanning tunneling microscope shown over here. It is showing, this is a micrograph of the scanning tunneling microscope showing individual hexagon-shaped atom arrangement. So these circles, each of them is an atom, and this is a hollow space. And atoms are arranged in a pattern in this compound. And this space is the distance of 100 angstroms.